Hey, this is Brock Lemiers, and in this video we're going to continue looking at circuit analysis techniques using Kirchhoff's current law, Kirchhoff's voltage law, and Ohm's law. And we're going to do an example where we look at a single loop circuit and come up with our first two kind of shorthands for determining the equivalent resistance of a series combination of resistors and also a voltage divider. So to kind of review, circuit analysis is where you have a circuit and you know the topology of it, and almost always you know the values of the resistors and the voltage source. And what you're trying to do is figure out unknown variables in the circuit, specifically the current that's flowing through the resistors or through the loops, and also the voltage across all the components or elements within the circuit. And we have three basic laws that allow us to write equations so that we can try to solve for the unknowns. And we have Ohm's law, which is V is equal to IR. We have Kirchhoff's current law, which basically states that the sum of the current into a node is equal to the sum of the current out of a node. So current in equals current out. And Kirchhoff's voltage law, which says that the sum of all voltage rises and drops around a loop in a circuit is equal to 0. So, or said another way, the sum of voltage rises is equal to the sum of voltage drops. So let's take a look at an example where I'm going to solve for a circuit that has three resistors in series. And what we'll do is we'll try to figure out if we can kind of use Kirchhoff's or use these laws to try to figure out what's going on in the circuit, and then also kind of try to derive some relationships about how we could combine the resistors in series and how we could potentially find the voltage across any of them just really quickly. Okay. All right. So let's take a circuit. Let's go ahead and just say we have a 9 volt voltage source, and what I'll do is I'll do all the equations with respect to a variable name, so Vs, and let's go ahead and say R1, and then we'll do R2, and then we'll do R3. And what we're going to do is we know R1, R2, and R3. Okay, so let's say that this is 150 ohms. Let's say this is 200 ohms. And let's say this is 300 ohms. Okay, and so when I look at this, I can immediately start trying to see what do I want to know and what do I not know. Okay, so what I want to know is what I don't know. So let's take a look at it. First and foremost, you can kind of just by inspection look and say, you know what? The current into this node is the current out of that node. It's the current through the resistor. It's the current through this resistor, the current through this resistor. There's only one loop. And so that means that the current through everything in here is going to be I. And when I draw that circuit like that, that loop, I also have not only defined the direction of I that I'm going to solve for, but I've also defined my loop direction. Okay, so I have one loop, and that's going to be the current right there. So if I look at what is unknown, okay, I want to find I. All right, well, what else do I want to find? Well, I also would like to find the voltage across R1, the voltage across R2, and the voltage across R3. So I actually have V1, V2, and V3. And then let's say what is known, and that is we know Vs, we know R1, we know R2, and we know R3. So you look at this and you're like, this is too much. Okay, I mean, we have 4 variables, and I have 4 unknown variables. I need to actually write 4 equations to try to solve for these. So this is 4 equations. So this is a lot, right? Well, it turns out that it's not terrible, and the reason is that we have KVL and KCL. First of all, let's write, KCL is actually not that important in here other than noticing that there's only one current flowing. So I know that the current flowing through all the components is I. So I did use KCL just to make that observation, but I don't even really need to write an equation for it. It didn't give me an equation. Let's do this though. Let's write an equation for KVL. Okay, this is Kirchhoff's voltage law, and I'm going to write it for around this loop. So remember that I'm going to go around the loop, and anytime I have a rise, I'll put it over here. Okay, and anytime I have a drop, I'll put it over here, and the sum of the rises is equal to the sum of the drops. And so let's start here. I have an arrow going clockwise, and so if I go from minus to plus, I'm going to have a rise. So my first thing I'm going to come across is Vs is on the rise side, and then I'm going to drop across our V1, from plus to minus. Okay, so that goes over here on the drop side. And then I'm going to drop from across V2. So I go plus to minus. Now I'm V2, so I'll tally that up over there. And then I'm going to come across here, and I'm going to go from plus to minus. And so I have V3 is a drop also. And I have my first equation. Okay, so I have the equation right here. I feel pretty good. I got my first one. Okay, all right, now what else can I do on here? Well, you know what else I can do? Why don't I just write Ohm's Law? Okay, so let's do Ohm's Law at R1, R2, and R3. So what does Ohm's Law say? Well, Ohm's Law says that V1 is equal to I times R1. And I came from this definition of the variable of the current that flows through the whole thing. Okay, piece of cake. Not too terrible. Ohm's Law at for V2 or across R2 is V2 is equal to I multiplied by R2. Okay, no big deal, no big deal. And then let's finally do Ohm's Law on resistor 3, which says that you have I times R3. Well, lo and behold, I have just very rapidly wrote 4 equations. So this is unbelievable. So I actually have 4 equations that relate my 4 unknowns, which are V1, V2, V3, and I, in terms of what I do know, which is Vs, R1, R2, and R3. And you go, okay, now all I need to do is start plugging them into each other. And it's like, oh, well, this is going to take forever because this is like simultaneous equations. And it's like, but guess what? This one's actually kind of simple because I plug V1 into there, I plug V2 into there, I plug V3 into there, and I can now write this equation that looks like this. Vs is equal to V1, which is I times R1 plus I times R2 plus I times R3. You're like, okay, this isn't terrible. Let's like check this out. I can actually kind of reduce this thing down too. I can say Vs is equal to I, pull I out and go R1 plus R2 plus R3. And look at this. Now this is really cool because I am trying to solve for I. I have actually isolated I immediately. This Vs is a known, R1, R2, R3 are knowns, and I is unknown. So I can immediately come down and find my first variable value by saying I is equal to Vs over R1 plus R2 plus R3. And you look at that and you're like, this is awesome. Well, let's plug in our values. I is equal to, Vs was 9 volts over 150 plus 200 plus 300. And I can actually put that in let's get old reliable out here. And I've got myself, let's see, I'll just do this in my head. 150 plus 200 plus 300 is equal to 650. So it's basically 9 divided by 650. And that is equal to 13.8 milliwatts. So I got 13.8 milliamps. Okay? It's like, wow, I did it. I just solved for my first value right there. And it's like, okay, that's great. Well, guess what else we have? I already have Ohm's Law for R1, R2, and R3, and I can find V1, V2, and V3. So now it's even simpler because I can just come down here and I can go V1 is equal to 13.8 milliamps times 150. Okay, so let's do that. So we come over here and I say, there's my current right there. And I'm gonna go times 150. And I got myself the voltage across R1. And it's like, this is pretty sweet, 2.07 volts. And then I can say V2 is gonna be equal to 13.8 milliamps times 200. And what's that? So I'm going to come up here and do, let's see, I'm going to do a little bit of nothing. I was going to try to undo that actually what I'll do is I'll go divide by 150 to get back to my regular current. So now I'm going to take that and I'm going to take my current times 200 and I've got 2.769 volts. And then finally, V3 is equal to 13.8 milli times 300. And then if you have an undo on your calculator, you can go back on this, but I'm just going to do this. I'm going to go divide by 200 to get back to my original current. And now I'm going to multiply that by 300. So I go times 300 and I get 4.15 volts. It's like, wow, that's pretty awesome. So I did it. I actually solved pretty quickly, honestly, for 4 variables in this circuit. Okay, so I had 4 variables, 4 unknowns in this circuit, and I solved them by writing 4 equations using Kirchhoff's voltage law and Ohm's law 3 times. And then all I did was plug them into each other, and I solved for everything that I wanted to know. It's like, wow, this is pretty amazing. If I was to just verify Kirchhoff's voltage law and said, is the sum of the rises equal to the sum of the drops? If I add these all together, guess what I end up with? I get 9 volts. And that is absolutely the exact amount that I had on this right here. So it's like, oh, this is pretty amazing. All right, so let's do something else. So we just solved a circuit. Okay, we just absolutely did it. And what I want to do now is let's take a look at what we know or what we can do with these equations. Okay, so the first thing that I want to do is try to figure out if I can figure out what the equivalent resistance is of series resistors. Okay, so this is going to basically be combining series resistors. Okay, and I actually have everything that I need right now to do this. Okay, so the first thing I need to kind of think about is this. I have these 3 resistors, and let me just draw them as like a chain here, just because it's a little bit easier to see. So I've got R1, R2, and R3. And I know that Ohm's law is equal to V is equal to IR. So one of the things you can always do is you can say that you can find the equivalent resistance by saying, okay, what is the voltage across this entire thing? Okay, so let's call that VEQ. And then we can say, what is the current through all of these? And I can call that I or IEQ if I wanted to. But really, if I wanted to write this equation, I could say that the equivalent combination of these resistors will be now written as VEQ equals IEQ times this thing called REQ. And if this is true, if I know VEQ, which is the voltage across these 3, from this node to this node, and I know IEQ, which is this, then I can lump this thing into one equivalent resistor, which I'll call REQ, and Ohm's law still absolutely holds. So really all I need to do is say REQ is equal to VEQ over IEQ, and I just need to now go figure out what the equation for that might be for this series combination. Well, let's take a look at this. One of our first equations that we wrote was this one right here. So when we plugged everything back into each other, I was given this guy right here. Well, look at the form that that's in. I could just take that directly down and say VS, which is what VEQ is, right? I mean, it is what is the voltage is across these 3 resistors in series. So I can say VS, and I can divide both sides by I, and I get I, and then I am left with R1 plus R2 plus R3, and that by definition, that ratio is actually equal to REQ. And so this is fantastic because what I can do is in any circuit, I can actually, or any series combination of resistors, I now have derived that they combine by summation. So if I looked at this and I said, what is the series combination or the equivalent resistance of this series combination of resistors? It's simply R1 plus R2 plus R3. And it works for an arbitrary number of resistors. If there's only 2 in series, then the equivalent resistance of that is R1 plus R2. The equivalent resistance of this combination is R2 plus R3. And there's actually a generic equation for it where you can say it's the sum of all the resistors. So it's just R1 plus R2 plus R3 plus all the other ones up to the end of the number of resistors. So we have just derived how to combine resistors in series. And I did it all with this simple test circuit that had 1 loop and resistors in series. Okay, fantastic. All right, well, that's kind of clever. It's pretty clever. And so now let's take a look at this. Let's take a look at what we could do if we wanted to find the voltage of each of these very quickly. Okay, and this is actually this is a special circuit called a voltage divider. Okay, and so a voltage divider is anytime you have a circuit configuration like this where you have one voltage across a series combination of resistors. And I want to directly find V1 or V2 or V3. Well, notice that this thing sits right here. Okay, so I have these three Ohm's Law equations right here. Well, look at what I have down here that I just derived. Well, I just derived this, right? So I just derived, let me write it a little bit different. So I have this right here where I can come along and I can say that this right here, I want to plug I into this guy and have it be in terms of what my knowns are. Well, look at this. I can divide both sides by I and I get Vs over R1 plus R2 plus R3. And all I need to do is plug that I into these equations. So let's write it and see what I get. Let me rewrite this first equation. V1 is equal to, let's plug I in, so we get Vs over R1 plus R2 plus R3 multiplied by R1. Well, look at that equation. Let's rewrite that a little bit. Let's rewrite it and say Vs times R1 over R2, R1 over R1 plus R2 plus R3. That is pretty cool because it almost looks like if I have this configuration, I could simply say using a voltage divider relationship that I just take the resistor that I want to know the voltage across over the sum of all the resistors in series, multiply it by the source resistor across all of them, and that gives me V1. Let's try it again for the second case. So I go back up to my Ohm's Law. I got V2 is equal to I times R2. What happens if I write this one? V2 is equal to, and I'm going to plug in I, because I'm doing Ohm's Law right here. So I got Ohm's Law, V2 is equal to IR2. So I go ahead and I plug in I, which happened to be Vs over R1 plus R2 plus R3 multiplied by R2. So that's that guy right there. And look at this one. It's almost in the exact same form. In fact, look at what I do if I rearrange this. V2 is equal to Vs multiplied by R2 over R1 plus R2 plus R3. And look at that. That is also in this form. And so it turns out that this is called a voltage divider relationship. And this is when you see this circuit topology right here, so let me draw it right here. When you see this circuit topology of one voltage across three resistors or two or three resistors or four resistors, whatever it is, you can immediately find the voltage across any of them using this type of equation. So for example, if I wanted to find V3, okay, so let's write our plus or minus V3, I could just immediately come over here and say, you know what, V3 is equal to Vs multiplied by R3 over R1 plus R2 plus R3. And it's like, wow, that is unbelievable. Now, does it work? Let's try it. Okay, so I'm getting a little sloppy here, so I'm going to come over here. I'm going to come over here and I'm going to plug in V1. So V1 is equal to, so here we go. Vs was equal to 9 volts, okay? R1 was equal to 150, and then the sum of all three of them, which was 150, 200, and 300. So that's going to be equal to 150 plus 200 plus 300, and that is equal to a voltage, okay? So let's bring out old reliable here, and let's try to do this. So I just know 150 plus 200, that's 650. So let's do it. 150 divided by 650, okay, and then I'm going to multiply that by 9, and I got 2.07 volts. Well, what did we get when we solved it the other way? Look at that, 2.07 volts. They're the exact same answer, and I did it two different ways, but this way I used a voltage divider relationship. Do you think it works on the other ones? Well, let's take a look. What about V2? So here's my equation for V2. It's going to be 9 multiplied by what was R2. R2 was 200, so 200 over 150 plus 200 plus 300. And that is now, let's pop this buddy in here. So let's say 200 divided by 650, that's that, and then multiplied by 9. That comes out to be 2.07 2.769 volts. Well, what was it before? It's like, oh boy, here we go. Here's the answer we had before. The answer before is right here, 2.6769. Holy Betty, 2.679. It's the exact same answer. This is unbelievable. So what about B3? You're telling me I can find B3 that quick? Well, yeah, let's do it again. So here we have 300 over 150 plus 200 plus 300. So let's plop that into a reliable and say, okay, so I got 300 divided by 650 times 9, and I get 4.15. And I'm like, all right, well, 4.15. If this works, I really have proven to myself that the voltage divider works. And it turns out, oh, Betty, look at it, 4.15. That's exactly what I got here, 4.15. I have just now proven to myself that anytime I see a series combination of resistors, I can immediately find the voltages across them using the voltage divider relationship. So we did it. Here's what we have actually accomplished. We have reviewed circuit analysis using our three main laws: Ohm's law, Kirchhoff's current law, and Kirchhoff's voltage law. We applied it to a series combination of resistors, and we were able to solve for our four unknowns using four equations that we got from our laws. But then we applied that to figuring out the series resistance of resistors in series, and it turns out that it's just the sum of all the resistors. So we were able to come up with our first kind of shortcut to doing circuit analysis, and that's combining series resistors. Then we looked at the voltage divider relationships, and we came up with our second technique as a second shortcut to quickly identify electrical parameters in the circuit when we have a series combination. So that is awesome. Okay, so the generic form of a resistive divider is simply whatever resistor you want to find the voltage of, put its value on top, and then do the summation on the bottom, and you got it. All right, nice work. That is circuit analysis, resistors in series, and voltage dividers. See ya.